Hello and welcome to the IMVC session on vision in automotive. My name is Ran Gazit. I work at General Motors Research Center in Israel. And our first speaker for the day is Dr. Ilan Kadar. He's a director of deep learning at Nexar, and prior to Nexar, he was leading the deep learning group at Cortica. He holds a PhD in computer science from Ben Gurion University. And he will talk about MultiTasks unified network for on-device autonomous driving.
Okay, thank you and good morning. 1.3 million people die on the road every year. 1.3 million fatalities yearly. And if we think about it, it's equivalent to 10 big airplane crashes every single day. And we cannot accept this. Nexar mission is to solve the problem of car collision at scale, and this is how we do it. Nexar builds the largest open vehicle-to-vehicle network by turning your smartphone into a connected AI dashcam. Nexar dashcam senses the environment around the driver, and the vehicle-to-vehicle network allows cars to communicate with each other and to sense beyond the line of sight. By leveraging deep learning with millions of driving miles collected by our user, our technology provides safer driving experience with the goal of solving the problem of car collision at scale before autonomous driving become a mainstream. Today I'll be talking about the work we have been doing over the last year to leverage deep learning, this powerful technique, in order to saving lives on the road, and specifically for developing a multitask unified network for advanced driver assist system. Driver assist system is the technology to prevent collisions, and it's all about corner cases. Corner cases are the many rare events that needed to be covered in your train data in order to reach from 95 accuracy level to 100 accuracy level or 99.999. And in Nexar, we built a dedicated pipeline for collecting these corner cases. Our pipeline starts with a sensor fusion detector that's run on the device and is able to detect these rare events, for example, accident or outbreak. These examples are then uploaded to our server when they are processed by multiple deep networks with human-in-the-loop feedback. With this annotation pipeline, we are able to train our system. Then a domain adaptation is applied in order to create a specific network for each city of interest. For example, we have a network for New York, network for Tel Aviv, and for San Francisco, and many other countries. With this pipeline, we already collected more than 10 million corner cases of driving and more than 10 million annotated images from over 80 countries. Last ICCV, we also released, in order to advance the road scene understanding research, we also released part of this data set. We call it the Nexar data set and benchmark, which is the largest and the most diverse annotated data sets. It contains 50,000 annotated images with bounding box around vehicles and their category. For example, there is a car, there is a truck, a pickup truck, and a bus. And all this data was captured from over 77 countries. Now I would like to talk about the challenges for deploying the driver assist system on mobile. So first, you need to develop an efficient deep architecture in order to provide real-time warnings and in order to allow updates of the models over the air. Our network was inspired by work like SqueezeNet, YOLO, and MobileNet, and ShuffleNet, and the key idea is that the number of parameters in the network can be significantly reduced without affecting the accuracy level, and the goal is to find a saturation point when adding more parameters does not improve the performance. The second thing is multitasking. While running on mobile, you don't have the privilege to run a different network for each task that you have. All your tasks should run simultaneously on a single network while sharing all your computational resources across a single task in a single shot manner. And all this you need to run and without compromising the accuracy, which is critical for ADAS. In our case, for example, our network is able to detect objects at various scale, is a truck, bus, car, or a traffic light. Also, we are able for each task to recognize its attributes. For example, for vehicle, we need to detect their lane level position. And for traffic light, we need to be able to detect the relevancy to the driver direction and also their color state. And also all these objects, we would like to track them over time. Now, let's talk about what are the multitasks, what are the tasks that we would like our network to solve. So we divide the ADAS feature into 3 levels. The first category, which we called level 1, is referred to the standard feature that you will get with the standard ADAS. It's forward collision warning and lane departure. The second is a more advanced feature, it's called level 2, which are more advanced features like pedestrian warning and traffic signs recognition. And our technology expands this feature with a new category we call the level 3, which include more complex scenarios like traffic light recognition, traffic light countdown, lane level assist, police detection, accident detection in front of you. All this should be supported with a single network in real time on mobile. Now I would like to focus on 2 of these ADAS features. The first one will be the forward collision warning when we alert driver when he's about to collide with the car in front of him. And the second is traffic light recognition when we are detecting the traffic light that is relevant to the driver. Now let's talk about the forward collision challenges. So there are 2 challenges. The first one, you should be able to detect and localize the vehicles. And the category, for example, here is a car, here is a truck, or a pickup truck. You want to understand and categorize them. This is not an easy task, but the solution for this is very straightforward, and there are a lot of work around object detection and vehicle detection. So it's practically a solved problem. The second challenge is to be able, for each detected vehicle, to be able to identify or to recognize what is the relative lane position. Because in forward collision, we would like to determine if this car is relevant to our drivable path or not. And for example, here you can see that this car is relevant to our driving direction, this one is also, and all that is on the right lane, and so not relevant. And also the police car, it's not relevant to our driving direction because it's not on our lane. And the straightforward approach for this is to use semantic segmentation or lane curve detection. But this approach can work when you have a small data that you need to annotate, or when you don't have any mobile constraints and you have all the computational budget that you would like. On mobile, when you would like to have an efficient inference, we found that the best way to do it is to treat it as a classification problem. What do I mean by saying classification? That we are actually tagging, assigning a category for each detected bounding box. For example, this is a same lane, this is a left lane, this is a right lane, and this way our annotation is more scalable, we can scale it, and also in inference time it's very efficient because classification is very efficient for deep networks at inference time. Now I'd like to go over our network. So our network consists of 2 main components. The first one is the feature extraction component, which is composed of a convnet. And the second component, which we call single-shot road understanding, composed of 3 conv layers, one for detection, the second for classification, and the third for the relative lane classification. And all of these attribute recognition are running simultaneously on the mobile and allow us to run on iPhone 7 with a 50 millisecond running time and a model size that is less than 6 mega. But what about corner cases? For example, here you can see a car that is turning and switching lane. Or here you can see that the lane marks are not visible at all. So for this, we incorporated the focal loss approach from the best paper ICCV, and we find it that by using this, by leveraging this technique, we are able to focus our training on these hard examples and significantly improve the accuracy on these examples. Now I would like to show you some of the results running on mobile in real time of our network. And so we are able again to detect now the vehicles and weather and the relative lane position. For example, blue, all the detections that are colored with blue are for the left lane. Now, as this car changed to our lane, it's already detected as red in our lane. And here you can see this vehicle is identified, detected as a left lane, this is the same lane, and the green one as the right lane. Now let's take a look at this car. As this car changed to our lane, we're able to detect it immediately that it is relevant to us. And another example, this car, which is not in our lane, but as we are getting cut off by this car, we are able to detect it and to warn the driver about cutoff. Our second feature, we are able to detect the cell velocity. I will talk about it more in the Q&A, but yeah, we do. Okay, our second feature is the traffic light recognition. This is a very tricky feature because it's not enough only to detect the vehicle, the traffic light, but we also wanted to detect the relevancy of the traffic light. And this is not an easy task because in order to understand which traffic light is relevant to our driving direction, you need to understand all the context in the scene. For example, here you can see in the right image when there are 3 traffic lights. The 2 from the right are relevant to our driving direction because we are moving straight, and the one on the left is relevant to the left turn, for all the cars that are turning left. And in order to be able to recognize and to understand this, it's not enough to detect the traffic light. You need to understand all the context of the scene, and in this case, even the road marks. You need to understand, incorporate it into a single descriptor and to understand this. And this is a very tricky task. And what about multitasking, efficient multitasking? So there are a few challenges here. The first one, efficiency. We wanted to solve 2 tasks, the vehicle recognition, the traffic light recognition, but we wanted to do it efficiently, meaning that we need to share all the computational resources across all tasks. The second thing, we need to support multi-scale object detection because traffic light can be extremely small, can be even up to 5 pixels, and we want to detect those. The third challenge is multi-attribute recognition. For each task, we have a different attributes. For car, we have the attributes of relative lane position, and for traffic light, we have the attributes of traffic light state, and also the relevancy of this traffic light. And the last challenge, we train with multiple data sets, because each task has its own data set with its own corner cases that we collected through our pipeline, and we wanted to leverage all our data in order to train our system. So how can we do it? So in order to extend the vehicle recognition network for traffic light as well, let's see what we should do. The first, we need to keep in mind that in deep network, there is always a trade-off between localization and generalization. So the deeper you go in the network, you get more generalization, but it's come with a localization trade-off, meaning that your receptor fields are smaller and you're not able to localize well, especially small objects. So what we did is we added the detection layer, the conv layer that is doing the detection and the recognition of the state of the traffic light. We added it on top of intermediate layer in order to get more localization. But what about relevancy? As we saw before, the relevancy require more context, more generalization, so it cannot be on intermediate layer. So what we did, we put it on our last layer in order to leverage all the generalization of the network and the representation of the network to support this task, which requires all the context in the scene. And what about training? How you can train with multiple data sets? We found that the alternate rating, when we're training back and forth between these tasks, scale well even for more than 2 tasks. We are currently running it with 4 tasks. And the reason why it's scaling well is because most of these tasks are correlated with each other. This is the first reason. The second reason, the amount of data. When you have a lot of data, and we are talking about 1 million images for annotated imager per task, so the problem becomes much simpler, and you can do the multitask training in alternate training fashion without compromising on the accuracy level. But what about corner cases, where there is a poor visibility? For example, here you can see it's not clear which traffic light is related to our driving direction, which not. And here it's even more confusing, even to human driver. to understand if I should go straight or stop. It's very confusing, and traffic light can be very confusing sometimes. So how you can deal with such corner cases, with such scenarios? So what we did in order to solve this, our solution is to augment vision with active mapping, meaning that we are taking all our database. For example, in New York, we have 1 million intersection videos in New York, and we are running our network that is able to detect the vehicles, the traffic lights, and the relevancy, and we also added additional tasks for self-localization. So we are now able also to determine in which lane we are driving. And combining this together, the video and the network, we are able to model this intersection. This intersection, by the way, this one is the same intersection that was captured by 4 different drivers. So we're taking all this intersection, all this video of the same intersection, we're able to model this intersection, and we can detect the number of traffic lights. We can detect for each traffic light for which lane is relevant and for which also driving direction. And here, this intersection is very tricky because there are 2 traffic lights that are really close by. You can hardly see it in the night, but each one of them has a different meaning. And without this modeling, it's very hard to get a good precision here.
So, can I ask?
Yeah.
So you know which junction you are at?
Yeah, we are using actually on the mobile. You have all the GPS, all the location, and you actually have a mapping that we can connect with. Yeah, exactly.
GPS is still you have changes in 10 meters or 30 meters. It's good enough.
Yeah, that's why I will show you in this video. This is exactly why we are using lane level localization in order to understand in which lane are you.
So you said GPS.
What? Okay.
Places the GPS is irrelevant.
If the GPS is not relevant. So there are some cases. First of all, we know 2 things. We know, first of all, the lane level positioning. We know, for example, here you can see we know the number of lanes. We are in the first lane. And second, we have a network to predict the distance from intersection. And we are using both these and the GPS in order to improve our localization.
Don't have GPS.
We have the GPS.
Places
If we don't have the GPS, we are mainly rely on our vision. And we have a network that predicts the distance from the intersection. We train a network to predict the distance from the intersection like we as a human do.
What is the prediction?
The prediction is not by a centimeter level, but on a meter level, below 3 meters. And we are able also to model, and it allows us, for example, here to model all the traffic light. And it's important to understand we don't need high definition maps. We are not focusing on building high definition map. We are building sparse representation, and we need the relations between traffic lights and the relevancy.
But do you rely on knowing where exactly you are? I mean, not exactly.
I need an approximation.
It's not a general purpose system. I mean, you need to have ahead information in order to do what you do. Right?
Yeah, we need to. So there are 2 scenarios. The first one, I can rely on the network, and it works perfectly. And there are some corner cases, in those corner cases, when we have such scenarios, we are not detecting. So we always aim for 100% precision rate. And for example, in this one, if we are not confident and if I don't have the location and only rely on the vision, so are not detecting this, and the recall is lower. But even purely, if you rely purely on the detection, on the vision without mapping, we reach to almost 100% precision with about 50% recall. So this is a huge.
What do you do in California when you have when you have a green on the left hand, but there's opposite traffic coming, you have to yield? What do you do in this case?
So in this scenario, this is a good question. In this scenario, we have actually the modeling of all the incidents in our database, and we're trying to analyze the routes. And until we get a confidence, this is an active mapping. If I don't have a confidence in the mapping, I'm not returning currently detection. I'm only returning detection where I'm confident and in the detection of the traffic light. It will be better, I think, if I show you the video, the demo, how we can do it. Yeah. So
Actually, I was okay, but
So I suggest to leave the questions and then maybe talk with Ilan outside.
no, but
Because
it
we
was
need,
relevant to the.
yes,
Yeah.
I understand, but we need to follow to the next.
okay, so just I would like to show our video how we can do it. So this is the video when you can see the traffic light that is relevant to us is detected, and this is the lane level positioning where we are able to detect it. Let's see how it's work. This is on mobile, purely on vision, without mapping. Let's take a look how we are detecting the switching lanes. And we are able, and it's purely run in real time, 50 milliseconds on iPhone 7, without any mapping. So it's important to mention that most of the scenarios are not the corner cases. The corner cases are the scenarios that we are dealing with mapping, but most of this is purely on vision. And all you can see is purely vision. We are doing a tracking. So we have in this network, in this component, we have a detection followed by CME network that is sharing the computation, is doing the tracking for each detected object.
The resolution of the video?
The resolution of the video, we are using 480 by 272 pixels for the image in order to run this real time. Okay, to conclude, this is a major part of our vision for solving the problem of car collision at scale, and more people download Nexar, and our network grows, our system becomes smarter and smarter, and we can save lives. And this is our amazing team that is responsible for turning our vision into reality. Thank you very much, and join us to make the road safer.